record on this computer, share screen. Yep. Okay, great. Week 7, 8, 7, 7. Let's go 7. Thank you everyone for coming. We're going to talk about negation today, I think.
Oh yeah. Okay.
It's a short chapter as far as I can remember. We did connectives last week, so products and logical and ors and disjunctions. So yeah, negation in Agda. Negation in Agda is usually defined as an infix symbol, not symbol and an underscore. And what that says is that not A says that given an example of A, I can give you an element of the bottom type or false. Obviously, if you remember from last week, the bottom type is empty. So if I can give you an A and you can give me some type of bottom, something has gone, something's gone very wrong. Because there is no type of bottom, so you shouldn't be able to write such a function. No,
you shouldn't be able to write such a function if A is indeed provable.
If A, yes, that is true. Yes, that is.
If A is the bottom type, there is a very good identification, right?
Yes, that is an excellent qualification. Yes, indeed, and that's the point, right? Because if you're proving something if you're trying to prove not something, then
It may not be well, but I can still split hairs.
yeah, no, absolutely right. Okay, evidence that not A holds, looking at this line, is of the form lambda x to the n, where n is a type bottom containing as a free variable type x. Okay, so it's just saying, okay, well, it's a function so that we can, if there is a witness to this,
so we can
we'll
construct a function.
Yeah, we'll have to construct a function to do this. Yes, and then they talk about contradiction or bottom elimination. It says, okay, well, if you have a function, well, if you have not A, so a function from A to bottom, and you have a element of type A, well, then you can produce a type bottom fairly obviously by applying the proof of not A to the element of A that you have. And therefore you can derive something type bottom. Interestingly, they don't. Oh, so yes. And if you remember from last week, if you have an element of type bottom as an input to your function, you can prove anything, right? By pattern matching on the absurd, on the two round bases for the absurd pattern match. You can use it to derive anything.
And also the clever thing you showed us of actually getting rid of nonsense cases as well. Because pattern matching has got smarter about not even needing to record some of these things, which is interesting.
Yeah.
We will step over the paragraph that says we set the precedents because it is an open issue in the library that the precedences are all broken now. So
only a little broken.
yeah, but in a slightly crucial way. Anyway. Wow.
Okay. So yes, the precedents, you want it to be less than conjunction, disjunction, all the other things, and then you also want it to interact with all the other types in the entire of mathematics in a nice way.
I'm not sure there is a consistent.
No, there's not. That's exactly.
Sure it's circular, actually.
Yeah. So set some fixity to it that means it parses nicely. Okay. So then moving on to discussion of what axioms to do negation are actually valid in Agda. So in classical logic, there's A is equivalent to not A, but only one direction of its implication holds in Agda. Namely that A implies not A, but not A does not imply A. How much detail? So yeah, so if you have something of, so you can introduce not, so if you have something of type A, and what we want is a function that as a first argument takes a function that goes to the empty type and returns the bottom type. So in particular, so we take in something of type X, we want a function, takes in a proof of not X, and we need to return the bottom type. Well, we can just apply not X to X. Is everyone happy? Is everyone happy why that construction is valid? Okay.
I'm only slightly panicking about the lack of white space in the pattern matching lambda. Shouldn't there be a space between lambda and the brace?
No.
No.
No parsing. Lambdas can be.
Oh, okay.
Braces are special characters. They're reserved.
Yep,
You can't use a brace as an identifier on its own.
No.
And therefore,
That's okay.
therefore that parses just fine. It's one of the few characters that does that.
Mm-hmm.
There's really not very many characters. I think bracket is the only, brace and paren is the only characters that aren't white space sensitive, and the parser will.
Semicolon.
Semicolon.
No.
You can use semicolon in names though, can't you?
God, can you?
In identifiers, I think. Okay. Or maybe they use the special Unicode semicolon in names. I don't know. Okay, yes. So it's a good question, but yes, it's not white space. That's fine. Interesting that they don't try. So what would be the problem if you had not A? Let's open Agda. Let's have an explore, unless anyone objects. Let's try and prove not A implies A and see what problems we run into, because maybe that would be.
It can't really start very much.
You can't really start very much because yes, you need.
Well, A is any, right? Any type, polymorphically quantified. You know nothing about A, so how can you get an A? Right? You're trying. What they give you is a not A, so some sort of a function space, and what you need to produce is an element of an arbitrary type
to apply that function to it.
Well, you are trying to construct an A, so you are trying to construct an element of an arbitrary type.
Yeah.
And the only thing you have on hand is some sort of a function that, okay, it produces an empty, so the only way you
if you can produce empty
could proceed would be to do a bottom element on the application of that function.
Yeah. But then you need to provide the argument to that function, which is something of type A.
A arrow bottom.
Yeah. I don't think that logic is completed. Okay. Is everyone happy with that?
It's not really a.
Is everyone happy with that explanation about why you couldn't produce an implication in the inverse?
It's not really an explanation, right? The explanation would be a sort of independence theorem, right? Or some sort of.
No, but it's an explanation for why this formalization of not, right? This particular formalization of not in Agda as a function to the bottom element.
I mean, I think it's a very, very sort of informal and hand-wavy explanation, but I mean, you fail, but it's not really clear.
That
it's impossible because generally.
I mean, you can show that it's. Like you can show extruded middle from it, right? So
well, yeah, but that's still.
Then you have to show that extruded middle isn't derivable.
Exactly.
Right?
Like I mean, like the explanation is there, but I mean, if you believe that extruded in the middle cannot be proven, then you also.
Let's ask the TV audience, are you happy that intuitionistic logic forbids certain inferences?
Yeah, I mean, in fact, the thing that bothers me is that people are not happy with that argument that you obviously can't do it because you've got nothing with which to do it. That seems perfectly sound to me. I don't quite see why there's anything hand wavy about that.
Well, it's because you have things like bottom element, and it's like in general, it's quite difficult to actually show that you can't possibly do it, right? So if you want to prove that you can't possibly do it, you have to either build some sort of a model where it will not hold or something like that, right? Or have some sort of very restrictive proof system in which you can't construct.
I mean, maybe if I'm happier than I'm supposed to be, I should just keep quiet and shut up. But it seems to be you can kind of see, if you were going to construct a thing, there would have to be a sort of last stage at which you somehow constructed an element of A. And given that you don't know anything about A, you know that you can't do that.
Yes, I would be reasonably confident that you could say, suppose there were such a proof, then because it's of functional type, it must begin with a lambda. And then that lambda must have an initial argument of type not A. And then how do you produce an argument of type not A? Well, only by applying, what would that, there's probably an argument based on normal forms. I'm now suddenly backing out of that. I think there ought to be.
Yeah.
In a sense, for the same reason at the meta level that we accept that there are no proofs of false. Because there are no canonical forms.
Yeah.
We expect if types are inhabited under no assumptions, they have a canonical form. What would the canonical form be? Oh, we can't have one.
Yeah.
Yeah.
But making those arguments clean and tidy is actually often a little bit more subtle than one likes.
I mean, I think you'll generally need to do some sort of capitalization or something, right?
Well,
to get
you're saying that there must be a normal form of any proof.
Yeah.
So there's an oracle outside that we're going to wave our hands with.
Yeah. So
but yeah,
that's the extent of hand waviness I was sort of talking about earlier. So yes.
Okay.
Okay, so then go on and discuss, well, okay, if you add extra negations to everything, then it is provable because we can introduce them. And then they go on to, yes, contraposition, which is another useful function for deriving. Yes. If you have A implies B, then you can prove that not B implies not A. And yes, well, what's a proof? Well, you have a proof of taking a function f, and you take in you want to construct a function from not B to not A, so you take in something of not B, and then not A. If this is a common pattern in Agda, and I'm sure other things, is that you're trying to prove not A, so that you take in your function, actually, when you expand this, right, this is actually a function from A to bottom. So you can take in an element of A on the left-hand side of your function declaration. So this is the element of A. And then on the right-hand side, we're not trying to prove not A, we're trying to prove bottom. So in some sense, once you expand this out, it all makes sense once you expand the definition of not A out. So we're trying to prove something of type bottom, so we have to do not. The only way we can produce something of type bottom is use proof of not. So we've got not B, so we need to produce an element of B. Well, we've got an element of A and a function from A to B. So we're good. Yes. So inequality. X does not equal y is simply not of x equals y. So if we have a proof that x is equivalent to y, then we can produce something of type bottom. Okay, and now there's something slightly more interesting. So if we've got concrete values for this, so for instance 1 does not equal 2, we want a proof that they're not equal. So what does this expand to? This expands to 1 equals 2 to bottom. So we need a function that takes in an argument of 1 is equivalent to 2. Therefore, right, the only inhabitant of equality of triple equals is therefore, right, which is, says that x is equal to x. Agda can automatically see syntactically that 1 is that's, well, 1 which detriggers to suck of 0 and 2 which detriggers to suck of 0 cannot possibly match that form. So it knows that there's no constructor of type therefore isn't valid there. So it knows that there's no type constructor there. So it knows that you can do an absurd pattern match here and derive the answer. So this is, it depends whether you, yeah. So this, you could write it this way. So this is a lambda with an absurd pattern match, which I'm not sure we've seen before. I think we've only seen absurd pattern matches in the left-hand side of function declarations. But you could also write this as, you could also move the absurd pattern match on the other side of the equals.
And you don't get an equals.
And you don't get an equals, so you could also write
underscore parent.
Yeah, you could also write that as well.
Are you okay with that, Perdita? Your face registered.
Yeah, you talked about absurd pattern matches in the session that I missed when I was away, I think. So I've got some catching up to do, but don't mind me. I will turn off my mic and make a note that I need to catch that up.
No. So, I mean, absurd pattern matches are pretty simple. It's whenever Agda infers that there can't possibly be a valid constructor there, you don't have to provide anything. You can just write these two parens, which means you can't match on anything. And because you can't match, because there's no valid inputs to the function, then you know that you don't have to provide a right-hand side to it.
Okay.
And so there is no equals and there is no right-hand side on the right-hand side of the equals.
Yeah.
Because it's just, it can't even be, right?
Yeah.
You can't get there.
You can't be in this case.
Yeah. Okay.
Obviously, this is a really kind of degenerate example where you're providing an input that can't possibly be. In many cases, you'll have some of the cases. So for instance, if you have a proof, if you have a proof that works for any natural number greater than or equal to 0, sorry, greater than 0, so any non-zero natural number, then in the 0 case, and you take in a, so for instance, if you take in a proof of x greater or equal to 1, then p of x, and you'd have one case where you have the absurd pattern match for 0, right? And then you'd have suck of x as the other pattern match. So you'd still have absurd, but one of them.
Yeah.
Oh, in fact, I'm almost going to talk about this. Okay. Oh, yeah, first use of absurd pattern in lambda expression. I just said. Yes, this is showing it with concrete. So we've shown it with concrete numbers. It works equally well with abstract anytime that it can deduce that they're not equal, even if you don't know the exact concrete representation of the term. If there's variables in them, free variables in the expression, then as long as they're not syntactically equal, it will also deduce the absurd. You can also use the absurd pattern. Okay, given the correspondence of implication to exponentiation and false to the type of no members, we can view negation as phasing to the 0 power. Okay. So 0 to the n equals 1 if n equals 0. So if I'm trying to work out if there's something profound and deep here, or whether this is. If
I don't know. I think the authors think there's something profound and deep. That they want the arithmetic of the type constructors to have some analog in the arithmetic of finite sets. I'm unmoved by the analogy, but perhaps I ought to be slightly more sensitive to it. Yeah.
Okay, well, unless if anyone can explain the deepness of this statement to us, then please go ahead. Otherwise, we'll move on unless anyone has. Cool. Interesting. So they're saying there's exactly one proof of bottom to bottom.
Well, if you assume extensionality, sure.
Yeah, that is fair and possibly interesting.
Yeah. Okay, if extends, but of course, if we remember, extensionality isn't valid in Agda's system. So it's a bit of an odd statement because in Agda's system there are two proofs. I mean, there are two proofs that Agda considers distinct. One which you just pass the element of bottom across, and one which you say, okay, well, it can't be. You can't. That first element can't exist. So therefore, I can produce some other bottom element on the right-hand side. So logically, it's one where it preserves this fictitious element of bottom, and one that conjures a new element of bottom on the right-hand side. Not that such element exists, but that's the distinction in Agda's head.
So for Agda, the two proofs are distinct.
Yeah.
Okay.
No. Well,
no.
Because there's some.
No, calm thoughts, everyone. Let's go to a browser, the buffer, and let's just write for all x of type bottom. Oh God, what do I want to write? I will say x equals the empty bracket, but I can't do that. So for all x, y, x equals y.
Like that?
Yeah.
No one has ever commented that it takes like 50 characters to import equality from a standard library, but I feel like someone.
No one really commented on that.
No one has ever commented. No one has ever commented on that. No.
So I think if you put x in the hole.
Hang on, x. So you want both of the arguments?
Well, one will do.
One will do.
One
okay.
will do, but put x in the hole, and then do Control C, Control C. Yep. Okay, there are no elements at bottom, so there's nothing to prove here.
Yes.
So
I agree. So that's one of the proofs.
right, but one of the things at hand was that you said there are two possible functions from bottom to bottom.
Yeah.
One which takes the proof and returns it.
Yeah.
And one which ignores the proof and returns the magic
Construct. Yeah.
conjured
Conjure.
out of nowhere. But you could argue, and indeed the extensionality argument refers to this, that even those two proofs at bottom, namely the one I hold and the magic one, necessarily are equal propositionally, because they couldn't be not equal, because if I have one or other of them, I can prove anything. So in particular, I can prove that they're equal.
Oh.
Right, so these two functions, in a sense, are returning arguments.
No,
which
that's.
can't be distinguished propositionally.
Yeah, well, but can't be
But
distinguished does not really cut it for propositional equality of functions, does it?
No.
Yeah.
No.
So this is again sort of assuming extensionality to some extent.
Indeed.
So I'm sort of wondering, because it sort of feels that at least in some conceivable variants of the type theory, these could actually be the same function due to some eta wrangling, right?
Yeah.
But I'm not sure exactly how much eta Agda does. Could you just try to write the two functions and check whether REFL proves their equality without extensionality? Just in order to see whether it, but without extensionality, just
Yeah.
right?
Sorry, I'm just trying to copy
sure.
this. Okay, so it expands, but it doesn't. Yeah.
Okay, so
okay,
Yeah.
So there's not enough eta magic under the hood, if indeed that would be.
So, okay, maybe. So there's a proposal. Is it a proposal or has it been implemented? I can't remember. But that has been implemented. So there's a proposal to make the bottom type irrelevant, runtime irrelevant, or compile time irrelevant. One of the two. So mark to Agda. There's special marks you can give to Agda that says, okay, this argument can never affect any of the resulting type. You can never case split on this argument, basically, at a high level is what you can mark it as. And in that case, with that proposal, then this would go through. And I think that's indeed one of the reasons why people are proposing. They want, in particular, they want any proof of, they want to have any proof of not, any two proofs of not A to be equal, I think is the motivation. To be definitionally equal. So if you're proof of, and that's what they want. And you can get that by marking in the definition of bottom set. They want to mark, what do they want to mark? Sorry, maybe this is an uninteresting detail. Yeah. No.
Maybe the issue isn't open.
Yeah. Okay. Anyway, but there might be extensions to Agda's type theory that the base Agda type theory that Agda implements that would allow you to prove this. But
so if we think of extensionality, the extensional equality of functions, then of course the two are equal, right?
So yeah, so this is exactly what people want to prove, is that if you have two proofs of not A, then the proofs are equal, and by default you have to use extensionality. It's a proof of negation. Is it a proof of negation they want to mark irrelevant?
Yeah.
Anyway,
formulae more generally.
Yeah. Anyway, okay. So show that it's irreflexive. The exercise. So that involves proving, and the definition of irreflexivity is if x is less than y, then x is not equal y. I guess we can try and do that. Might be. Let's get some imports. Wait, well, type text data.that.properties, which is large.
You probably want relation.unary.
Goodbye.
Ooh, do you want to write that?
Well,
Well, you can. I mean, yes,
Okay.
you've written it. Of course you want. Yes.
okay. Yeah, sorry. Okay, let's write the actual definition of irreflexive rather than using the standard library version. So if x is equal to y, then
Implies what?
this is not what I meant to write. How about that?
Yeah. Or just put the not in.
Or the not in. Why not? But then I have to have an extra import.
Oh
Yeah, we need a prelude or some, but then the problem is I don't want the arguments about what would go in the prelude, which I know would last several years and
Yeah.
be actually within the last years it would be infinite.
So I would have always short-circuited this for the sake of the filter readers and written for all n, not n less than n.
Yeah, sure.
Just because that's what I'm like.
Ooh, what did I do? No.
Just double click on the
How did I do this? Thank you. Good shout. Yes.
Not a, yeah.
Okay, and let's make it another piece. Okay, so let's have a look. So we want to prove. Okay, so how do people, non-experts in the room, think? Well, maybe everyone's an expert now. That's what do the non-expert experts think the best approach should be to this? No, we can
No,
match.
I think it's the only available option. So,
When people ask, you feel like maybe there is, you know, if I say
A
much,
secret
people
trick.
say no.
yeah, well,
Okay.
no, I mean it's a great hump to get over with undergraduates. You know, pattern matching is your friend, and sometimes it's your only friend. So yeah.
Okay, let's pattern match on n. So what do we have to prove here in our goal? We have to prove not 0 less than 0. And if we expand this out even further, yeah, 0 less than 0.
Okay, how is the strict inequality defined?
So,
Oh, in a horrible way.
Yes, James has it.
Everyone cry. Ugh.
Okay. Fine. Yeah.
so in particular, maybe we'll get fed up and in version 2 we'll break everyone's. We'll go full hog and break everyone's Agda code ever and actually fix the definition. Yes. So in particular, we need, let's have a look. So let's take in, as we have an argument, as we're taking in the function, let's take in an argument. Let's take in that proof of L so we can pattern match on it. Interesting, we don't have to add it there. You can, this is unlike Haskell, you don't have to have the same number of arguments in every case. So we'll leave it out for a minute. We will need to add it, but just as a demonstration. Okay, so what's our proof? Well, a proof of 0 strictly less than 0 is actually equivalent to a proof for is 1 less or equal to 0 from the definition of strictly less than as suck of the left-hand side, 1 plus the left-hand side.
We have something that's impossible.
And yeah, there is no proof of 1 less than equal to 0. There is no constructor. So we can ask, okay, well, let's pattern match on L. I mean, we could, yeah, okay, let's pattern match on L. And it says, okay, well, Agda says, okay, I can't possibly have a proof of 0 less than equal to 1, so I can match it with the observed pattern.
Okay.
So let's have the same thing here. So again, we need a proof of suck n less than equal to suck n. So let's add that proof in as an argument. We don't need to produce something of type bottom. Let's play the same trick. Let's pattern match on L. Okay, well, it says, okay, we have a proof that suc n is strictly less than suc n. Well, it knows, okay, the only format it can be is a proof this s less than equal to s constructor that says, okay, if m is less than equal to n, then suc m is less than equal to suc n. So we have a new proof that, okay, so this is a limitation, right, of slightly of Agda's, is that Agda has now expanded this. It doesn't say n strictly less than n. It's actually expanded this in the context. So we don't get the same form of our type of our inductive hypothesis, but we essentially have the same inductive hypothesis, right?
Mhm.
So we can now recurse and say, okay, well, I know that there is no proof of n strictly less than n.
Mhm.
So I can, by a recursion, we've got strictly smaller. So we can conjure our type, empty type of type bottom by just making it one, by going one smaller.
And indeed, that's typical of proofs of bottom, is that you have a tail call on the function, and at the very bottom, it fails to produce anything, and says it can't be done. And in some happy cases, you can just obtain absurdity just from the tail call. There's a kind of infinite unfolding idea going on there. But here we do actually reach bottom because the patterns get down to 0.
Can we kill the first line?
Yes, so this is exactly what we were discussing last week about absurd, and James mentioned, in that Agda is actually pretty good. It will unfold definitions inside its internal machinery. It can unfold pattern matches up to a certain depth, and the default depth is 2.
Good default.
Because that covers about 98% of the proofs in the standard library, and there's and then the rest of the remaining 2% require a depth of 3, but we just set it to 2 and
So
have it
the
manually.
TV audience at home, watch what Matthew is about to do.
So because it automatically unfolds it to depth 2, if not given, then it knows that there's an absurd pattern here. So you can actually just delete that line, and it will type check just fine as a proof, because it knows that case can't possibly exist.
Is that not worth a BAFTA television award?
I'm not sure it's very helpful to the reader of the file.
It depends. So in this case, maybe not. In certain cases where you're passing in arguments, for example, that there's a lot of proofs that require for all n such that n is non-zero, p of n, and actually not having to write that 0 case, which is completely obvious on the type, or it gets worse when you have more constructors as well.
Yeah.
This case only has 2 constructors.
It also depends a little bit on how you read the file, whether you read it as a sort of, in a browser or interactively. Because here you can check what the constructors of n are and see what are the missing constructors. And okay, since there are no, the missing constructors are not there, then these cases are impossible, right? And I mean, the line doesn't really provide that much insight into why the case is impossible, right? There's 0 and the case is impossible. So, I mean, it doesn't really give you that, I don't think.
And provided there's only one reason for leaving out the constructor, we're good.
Yeah, I mean, otherwise Agda will complain.
Yes.
The pattern matches have to be exhaustive. So if there's missing cases, this means that these cases are impossible.
Yeah, the only time when you can admit cases is if Agda can show that they can't possibly hold. Yeah.
And Agda is pretty good at flagging. You've missed some cases.
Yes, you can't write. Unlike Haskell, you can't write partial. You can't write partial functions. So
I mean, you maybe can mask something.
yes, yeah, okay. You can probably, if you write something explicitly and give instructions to the Agda compiler for this function, non-terminating. But non-terminating disables termination checking. It doesn't determine case splitting. I haven't seen one.
Right.
I haven't seen I've never seen a pragma in use that disables. I'm not saying that there isn't one because there's about 200 different ones. But
yeah, I don't. Like at any rate, it would have to be something for interfacing with real world or something like that, right? Because if you're trying to prove something, you do want to consider all the cases. So.
Yeah.
But if you went back to it and took out the line.
Yep.
So. No, I was going to get on a hobby horse. Forget off the hobby horse. We have a summer school. Get on a hobby horse.
Yes. There's a few more exercises, but I don't think that they show. You can leave them to the audience. And they show anything deep that you haven't shown so far how to interact with it. Intuitive versus classical logic. I think, unless anyone particularly wants us to go into this discussion, philosophical discussion, we might skip before James sees something that he violently disagrees with. Okay, excluded middle. Okay, so this is, yeah, alternative axiom. This is classical logic. For any A, you can either produce A or a proof of not A. It doesn't hold in Agda because you need to be able to conjure up I mean, there is no way to conjure up something. It needs evidence, and there's no way to conjure up something arbitrary of type A, even if it does hold, even if A is true, happens to be true. In general, for an arbitrary one, you can't conjure it up. We can show that it is irrefutable. Show negation of the negation. Okay, so you can't prove that it's not true either. And it steps through the pattern matching. Anything of interest?
Well, there is the usual point of interest that you're using K with both int 1 and int 2.
Both in int 1 and what's it? Int
with both injections, right?
Oh, with both. Okay. With both, yes.
Right, so you take K, the sort of continuation that's supposed to give you the non-termination, and you have to use it both with, you have to try to fail and then succeed eventually, right?
Yeah, well, we can have a look at it. Maybe we can create a separate library for a prelude, and then I can hand maintenance of that off to someone else, and they can deal with all the argument. We can still have a prelude, but it doesn't have to be a responsibility of the standard library to decide what that prelude is.
Have many preludes.
Yes, exactly. Yeah. Okay, so let's have some pause. I'm not sure why I've done that. Okay, so we've got something of type not A or not A, and we want to produce something of type bottom. Well, the only way we can do that is apply what our proof of negation. So let's get rid of that so we're not cheating. Okay, so we then need to prove something of A or not A. So
I have to choose, right?
It's
difficult to produce something of any type, right? Of an arbitrary type. So the right hand side is the more
Yeah. So let's say, okay, well, we can't produce something of type A, so we've got to produce something of type not A.
And here at least we can take an argument, right? This is
What,
a function.
Yep, so this is a function from A to not. So we can now get something of type A. And again, we have to prove something type empty. Well, that's good because we now have an instance of A, and K is a proof of not A or not A, but we have A. So we can again apply K. And when we're now forced again to prove A or not A, we can, now we have an instance of A, we can give it.
So you do have to use both cases of the disjoint sum, and what's more, you have to use the thing that came from the second case as the argument for the first one. Right? Yeah.
Standard period, okay, stable. Yes. Yeah. And they ask you to prove all this. Prove that they're all equivalent. Each of these implies all the others. So yeah, 25, that's a bit of a mean exercise asking you to do all 25, but they're going to be very good.
Well, you could do them in a loop, presumably, can't you? That's what you usually do.
Yes. Yeah. You'd still have to write. Yeah. Well, it depends. Yes. If you do them in a loop and then you say right done, or whether they actually want anchor statements that each one improves the other, in which case you'd have to apply the loop. But,
yeah.
Yeah, and then stability for certain types. I mean, if the type is decidable, right, you can prove that not A implies A simply by so any type that's decidable, you can prove not A to A for, but not all types. Yeah, not all types satisfy that, but yeah. Should have any negated form that is stable, which is indeed it's an interesting exercise because that's exactly, well, uninteresting exercise because that's exactly what we've shown above is that not A implies not A. Okay, given that we have a guest speaker and we're going for lunch with them, we'll probably wrap up there. Does anyone have any last questions or comments or?
We enjoyed some amusement at Phil's expense in the last talk with his sprinklings of medieval reminiscences and logic. And what's funny is that there are no such reminiscences in this chapter. But that's just as well. And possibly also historically accurate. But it's entirely unobvious what the medieval logicians understood about negation. Given that a lot of these arguments were only formalized in the late 20s, 1930s, so less than 100 years ago. Amazingly.
Wow, we're almost 3 sessions away from finishing part 1. Good job. Okay, I'm going to stop recording. Cool.
Presentation 29 for the writing, so we've got a way to go.
Thank you, Bernadette.
Thank you. Bye.
Have a good.
Thanks. Bye.
Yeah. Bye.